There is a prison built into the architecture of the universe itself. It has no walls you can see, no bars you can touch, and yet every civilization in the cosmos, no matter how ancient or advanced, sits inside it, the speed of light. 186,000 miles per second. In the vacuum of space, nothing with mass has ever been observed moving faster. Not by a fraction, not by a whisper. The universe enforces this limit with an absoluteness that makes even the most audacious physics feel humbled. And when you really sit with what that means across the staggering distances between stars, between galaxies, it stops feeling like a scientific fact and starts feeling like a sentence. The nearest star system to our own, Alpha Centauri, sits roughly 4.25 light years away. That means light itself, the fastest thing nature permits, takes 4 years and 3 months to make that crossing. If you were aboard the fastest spacecraft humanity has ever launched, Voyager 1, which is currently crawling through the outer edge of our solar system at about 38,000 miles per hour, the journey to Alpha Centauri would take approximately 75,000 years, not centuries, 75,000 years. Our entire recorded human history spans about 5,000 years. You would need 15 of those histories stacked end to end just to reach the closest neighboring star at our current best speed. Now step back further. Our galaxy, the Milky Way, is roughly 100,000 light years across. The nearest large galaxy, Andromeda, is 2.5 million light years away. The observable universe stretches approximately 93 billion light years in diameter, and it contains somewhere in the range of 2 trillion galaxies. When you hold those numbers against the speed limit that physics imposes, the universe begins to feel less like a vast frontier and more like a quarantine. Civilizations separated by hundreds or thousands of light years might as well be separated by an infinite wall, because even at light speed, the travel time dwarfs any biological lifespan we can reasonably conceive. This is the cosmic cage. And for most of the history of physics, it seemed absolute. But here is where the story bends in a direction that is genuinely astonishing. Because Albert Einstein, in constructing his general theory of relativity in 1915, did something that even he did not fully anticipate. He handed physics a framework in which the speed limit applies locally, meaning at any given point in space-time, nothing moves faster than light through that space. But the fabric of space-time itself, the stage on which all motion occurs, is not bound by that rule. Space-time can stretch, it can compress, it can curve, warp, and under the right conditions, it can do something even more radical. It can fold. To understand what that means, imagine the universe not as an empty room filled with objects, but as a fabric, a continuous, flexible, four-dimensional sheet on which matter and energy leave impressions. A massive star curves that fabric around it. We experience that curvature as gravity. The Earth orbits the Sun not because some invisible force is pulling it, but because the Sun has bent the geometry of space-time in its vicinity, and the Earth is following the straightest possible path through that curved geometry. This is not a metaphor. This is what general relativity actually says about the nature of space and time. Gravity is geometry. Motion is geometry. The cosmos is a living, dynamic, curved manifold. Now take that picture and ask a different kind of question. If space-time is a fabric that can bend, what happens if you bend it sharply enough that two distant points on that fabric are brought into direct contact? Imagine you are holding a flat piece of paper. Draw a dot at the top left corner and another dot at the bottom right corner. The distance between them, measured across the surface of the paper, is significant. But now, fold the paper so those two dots are touching. The distance, measured through the fold, is essentially zero. The dots have not moved relative to the surface of the paper. Every inch of that paper still exists exactly as it did before. But by changing the geometry of the paper itself, you have made two distant points adjacent. This is the core idea behind what physicists call an Einstein-Rosen bridge, more commonly known as a wormhole. It was first described mathematically by Einstein and his colleague Nathan Rosen in 1935 as a consequence of the equations of general relativity. The mathematics does not forbid a tunnel-like structure connecting two separate regions of space-time. In principle, The equations allow for a shortcut through the geometric fabric of the universe, a passage that bypasses the ordinary distance between 2 points by threading through a different dimension of the geometry entirely. You would not be traveling faster than light through space. You would be stepping through a fold in the architecture of space itself, emerging somewhere vastly distant without having crossed the intervening distance at all. But here is where the physics becomes genuinely brutal in its demands. Because while general relativity permits the existence of such structures mathematically, actually constructing and maintaining one requires something the universe barely tolerates and may not tolerate at all. To understand why, consider what holds a tunnel open. If you dig a physical tunnel through the Earth, the tunnel collapses under gravitational pressure unless you shore it up with material strong enough to resist that pressure. A wormhole faces an analogous problem, but at a scale that makes the engineering of any human civilization look like arranging sand grains. Gravity, the very phenomenon that curves spacetime and makes the wormhole geometry possible, also acts to close the throat of the tunnel. The moment you create a wormhole, the tendency of spacetime is to pinch it shut instantly, crushing anything inside to a mathematical point of infinite density. To prevent that collapse, you need something that pushes outward against gravity rather than inward with it. You need what physicists call exotic matter, specifically a material with negative energy density. Normal matter, every atom of every star, every particle in every galaxy, has positive energy and positive mass. It pulls space-time inward. Exotic matter, in the theoretical sense required here, would push space-time outward, acting as a kind of scaffolding that braces the walls of the wormhole and holds the throat open against gravitational collapse. The question is whether such matter can exist in any physically realizable quantity. Here, the quantum mechanical picture offers a tantalizing but frustrating hint. There is a phenomenon called the Casimir effect, discovered experimentally in 1948, in which two uncharged metal plates placed extremely close together in a vacuum experience an attractive force. The explanation lies in the behavior of quantum fields. The vacuum of space is not truly empty. It seethes with virtual particle-antiparticle pairs, constantly flickering in and out of existence, a consequence of the Heisenberg uncertainty principle, which forbids any system from having a precisely defined zero energy. Between the closely spaced plates, fewer of these vacuum fluctuations can fit compared to the space outside the plates. This creates a small but measurable difference in energy density across the plates, and in this region between the plates, the energy density of the quantum vacuum is genuinely, measurably negative relative to the surrounding space. The Casimir effect is real. It has been confirmed in laboratories. It demonstrates that negative energy density is not simply a fantasy of the mathematics, but, and this is a but that carries the weight of entire star systems, the amount of negative energy produced by the Casimir effect is staggeringly small. The gap between what the Casimir effect produces and what you would need to hold open a traversable wormhole large enough for anything macroscopic to pass through is so enormous that it is difficult to even find an analogy that captures it. Physicists who have worked through the numbers, including Kip Thorne at Caltech, who developed the modern theoretical framework for traversable wormholes in the 1980s, found that the exotic matter requirements are likely comparable in magnitude to the total mass energy of entire planets, possibly entire stars, configured with negative energy density. The universe does not appear to manufacture this naturally, and we have no remotely plausible mechanism for producing it at the necessary scale. So where does this leave the question of what a sufficiently advanced civilization might be capable of? This is the point at which the conversation shifts from what we know to what the physics genuinely leaves open. And the honest answer from a physicist's perspective is that we do not know the upper boundary of what is permitted by the laws of nature. We know the laws as we currently understand them. We know what those laws permit and forbid at the energy scales we have probed experimentally. But the history of physics is a history of discovering that the frontier of the unknown harbors structures and phenomena that the previous generation of physicists considered impossible or fantastical in the 1980s, 1990s. The idea that the expansion of the universe was accelerating would have struck most cosmologists as implausible to the point of absurdity. Then in 1998, two independent research teams measuring the brightness of distant supernovae discovered that the universe is not merely expanding but accelerating in its expansion, driven by something now called dark energy, an energy density permeating the vacuum of space with properties that bear a striking resemblance in their mathematical structure to the exotic matter required to stabilize a wormhole. Dark energy has negative pressure. It pushes the fabric of space-time outward rather than pulling it inward. We do not know what dark energy fundamentally is. We have no quantum mechanical theory that accounts for it satisfactorily. But it constitutes approximately 68% of the total energy budget of the observable universe, and it has been present, apparently, for billions of years. The universe itself is threaded with a form of energy that defies the ordinary gravitational rules. This does not mean that dark energy can simply be harvested and redirected to hold open a wormhole. The physics of that would be extraordinarily complex, and the connection between dark energy and traversable wormhole stabilization is not established. But it does mean that the universe's energy landscape contains structures and phases that are genuinely exotic, genuinely gravitationally repulsive, and genuinely real. The door that says the universe forbids all forms of negative energy or gravitational repulsion has been taken off its hinges by observational cosmology. Consider now what it would mean for a civilization to operate on timescales and energy scales that dwarf anything in human experience. Our civilization is approximately 10,000 years old, measured from the earliest agricultural settlements. The universe is 13.8 billion years old. That ratio, 10,000 to 13.8 billion, is roughly equivalent to a single second measured against the span of 400 years. A civilization that began just 1 billion years before us, which in cosmological terms is not ancient at all, would have had 100,000 times as long to develop their understanding of physics, their mastery over energy, and their capacity to manipulate the geometry of space-time. The laws of nature do not change. But the depth to which those laws can be understood and exploited grows with time, knowledge, and technological capability. There is another avenue the physics opens that deserves serious attention here, and that is the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. Alcubierre showed mathematically that general relativity permits a geometry of spacetime in which a bubble of flat space is surrounded by a region where spacetime is contracting ahead of the bubble and expanding behind it. An object inside the bubble is locally at rest. It is not moving through space faster than light, but the space itself around it is being dynamically reconfigured so that the bubble effectively surfs a wave of spacetime geometry, arriving at a distant destination far faster than light would travel the same route through undistorted space. Again, the ship does not break the local speed limit. The road bends itself around the limit entirely. The energy requirements for the Alcubierre metric, as originally formulated, were calculated to be on the order of the mass energy equivalent of an object the size of Jupiter in exotic matter with negative energy density. More recent refinements to the geometry by physicists Harold White and others have brought those theoretical estimates down substantially, though they remain far beyond anything humans can produce. But the direction of those refinements is significant. The required exotic matter has been shrinking as physicists develop more sophisticated geometric configurations. Whether it can be brought within reach of any physically achievable technology remains genuinely unknown. What we can say with confidence is that the laws of general relativity do not simply slam the door on these possibilities. They open a narrow but mathematically consistent corridor through which, under the right conditions, with the right physical resources and the right understanding, motion through the cosmos at effective rates far exceeding the speed of light is not logically self-contradictory. It is extraordinarily difficult. It may require physics we have not yet discovered. It may require energy sources that have no parallel in our current technological civilization. But the architecture of the universe does not explicitly forbid it. And that distinction between what is hard and what is impossible is one that physics takes seriously. The question of what an alien civilization might have found is, in one sense, A question about the depth of the universe's physical law book. We have read perhaps the first several chapters. We have discovered quantum mechanics and general relativity, but we have not yet written the unified theory that reconciles them. That reconciliation, whatever form it ultimately takes, whether it is string theory or loop quantum gravity or some framework not yet conceived, will likely reveal new layers of structure in the space-time fabric, new physical quantities that can be manipulated, new conservation laws and new violations of conservation laws we thought were absolute. Every major revolution in physics has expanded the space of what is physically achievable. There is no compelling reason to assume we have reached the last revolution. So here is what the physics actually leaves us with. The speed of light is real. The distances are real. The energy requirements for space-time manipulation are staggering and may involve forms of exotic matter that push at the very edge of what the universe permits. But space-time is not an inert backdrop. It is a dynamic, geometric, malleable entity. General relativity tells us it can bend, fold, and in principle, allow shortcuts that no local speed limit can prevent. A civilization that has spent 1 billion years reading deeper into the same